4.2, we're going to continue our discussion of derivatives here. We're going to be looking at one of the most useful things that differential calculus will do for us. One of the most useful things we can do with derivative, and that is find out where a particular function has a maximum value or a minimum value, and where that occurs and what that maximum and minimum value is. So look at the definition of maximum and minimum values, absolute max and absolute min, on page 269, the first definition in your section. You can see what it means. I mean, basically, if you have a graph here, let's say it looks like so, and this graph is over some, well, defined on the xy plane. You can see that if we the absolute max, if we go, say, from this point here, let's call it A, to this point here, let's call it, well, we'll stay with what the book does, call it E. The absolute maximum value occurs right here. This is the biggest value that our function takes on. It takes on this this value right here. The smallest value, the absolute min, is this point right here. That's really all you need to think about. The absolute max is going to be the biggest value of your function in some interval or over the domain of that function. The absolute min is going to be the smallest value of the function, all right, over some interval. Now, one thing I want you to notice, the biggest value occurred at basically a turning point where our function turned. All right, that was where our absolute max occurred. Our smallest value occurred not at a turning point, but at an endpoint of our interval between A and E. So if we label this point here C, actually let's label it D. All right, we say we had an absolute max occurs at x equals D, and the maximum, we would say then the absolute maximum value is the function at that point f of d. If this is the function y equals f of x, and then this point maps over to f of d. All right, we have an absolute min. We have an absolute min for this function. Where does it occur? Well, it occurs at x equals a. We have an absolute minimum value of the function evaluated at that point. So when we talk about the absolute min value, we're talking about the function at that point. We're talking about where it occurs. We're talking about the x value there. So again, the absolute max occurred at a turning point. The absolute min occurred here at an endpoint. And that's really where we're going to have to look for. We're going to have to look at where our function turns, and also we have to consider our endpoints as possible places for absolute max and min. You can see our right endpoint is neither a max nor a min. It's neither the biggest value in the function or the smallest value. But now there's some other points here. There's other places where it turns. If you notice, this point here, here, and here we have turning points. Now these are not absolute maxes and mins because they're not the biggest or the smallest points over our interval from A to E, over our domain of our function. But we can think of these as the biggest point. For example, this point, if we label this point B, f of B, what's the biggest value of all the x's in a neighborhood around B? I could take a neighborhood around B like so, and if I evaluate my function at all these x's in here, the function evaluated at B is the biggest. So we have a local max here. A local max because it's the biggest in the area. Similarly here we would have a local min. And this is both a local and absolute max. And this is a local min. It's the smallest value in an area in some interval around this point. F of that value is the smallest that it gets for any x value around that point. That's not the smallest value overall. We already established that that was A. So it looks like any of our local maxes and mins are going to occur where we have a turning point. Now what else is true at these turning points? Well, what's going to be true about the derivative? Remember, the derivative is the slope of the line tangent. What do line tangents look like? Well, if we're right at those turning points, the line tangents are going to be flat lines. What's the slope of all those going to be? That's right. It's going to be 0. The slope of all these things are going to be 0. So what does that tell me? Well, that tells me that if I take my function and we take f prime of, well, b, that has to be 0. What else? Now let's label this point C. F prime of C has to be 0. If we label this point as we already did D, we know here that f prime of D is 0. So let me block this off here. And let's see, we already used E. We'll call this F. F prime of F is 0. Kind of an abusive notation there. But again, any place where we have a turn here, well, that is a place where our derivative is going to be 0, and that is a place where we have a possible local max or local min. And that's what they talk about on definition 2. And in definition 2, basically we say what a local max or min is. So it's basically the biggest point in an area or the smallest point in an area. And then we talk about where we can find those local maxes or mins. Let's see, before we do that, let's look at the extreme value theorem on page 271. It's worth noting. Basically, all that extreme value theorem says is that if we have some continuous function on a closed interval from a to b, then f attains an absolute max value, f of c, and an absolute min value, f of d, at some number c and d in that interval. So it's very important to look at those examples in figure 5, figure 6, and figure 7. Figure 5 illustrates why the extreme value works. Extreme value theorem works if you have a closed continuous function. At some point you're going to have a biggest value, at some point you're going to have a smallest value, and it's always going to occur either at the endpoints or those places where the derivative was equal to 0, like we talked about. Figure 6 and figure 7 shows places where we don't have, if you don't have continuity, the extreme value theorem may not apply. For example, let me just sort of draw a sketch of kind of what we have in figure 6, where we have a little gap right here. Now this is well, this is not continuous on this closed interval. It's defined everywhere between, say, here's B and here is A. So it's defined everywhere there, but you can see we actually have no maximum value. If this value here is, say, 2, well, the function gets very close to 2. It never actually gets to 2, but it gets as close as you want. And so it can always get bigger because you can always get closer to 2. So it does not have a maximum value. It does have a minimum value, which would be this point right here. F of b would be the minimum value here. So your c and your d could be the endpoints, and a lot of times they will be the endpoints. But we need continuity in order for the extreme value theorem to apply. Okay, now let's go back to what we were talking about, where those critical values, where those extreme values can occur. And that brings us to Fermat's theorem, not his last theorem, just his theorem. And what does that say? Well, Fermat's theorem says exactly what we've been talking about earlier. It says if f has a local maximum or a minimum at c and the derivative exists at that point, remember derivatives don't always exist, even for a continuous function, then the derivative has to be 0. In other words, a local max for a continuous function where the derivative exists everywhere, a local max or local min can only exist at places where the derivative is 0. And we saw that up here. So a local max, local min, local max, local min, those only occur where the line tangent has a horizontal flat slope of 0. The line tangent is horizontal, so its slope is 0. And so the derivative at all those points, like we said, is 0, where we have those local maxes and local mins. Now, as the book points out, and it's important here to see that the converse of this does not hold. For example, they look at the function f of x equals x cubed. F of x equals x cubed. Notice here that the derivative, which is 3x squared, is 0 at 0. And that tells you also that the line tangent to the curve at that point is horizontal. The slope is 0. Yeah, but this is obviously not a local max, not a local min. It's not the biggest point in the area. It's not the smallest point in the area. If we go to the right, we have bigger values. We go to the left, we have smaller values. So just because a derivative is 0 does not mean it's a local max or local min. The other situation that they show, it's very important to point out, is something like the absolute value function, where you have a situation like f of x equals the absolute value of x. Remember that the derivative does not exist at x equals 0, although we do have a local min here. F prime of 0 does not exist because the slope of the line tangent as we approach from the left is -1, while the slope of the line tangent as we approach from the right is +1. Those two eventually have to, the limit of those slopes as we approach 0 from either side has to match up in order for that derivative to exist. So it doesn't exist, although we do have a local min at that point. So, two caveats here. Well, not caveats, but we're just saying that it doesn't work both ways. We could have a derivative that's 0, but not a local max or min at that point. We also could have a local min or local max where the derivative is not 0. Now notice here, though, that the derivative does not exist, and so we can say in definition 5 exactly what we mean by that. We're going to call those places critical numbers. So by critical number, what we mean is we need some value c in the domain. So by critical number, we mean this c here. That's our critical number, such that either the derivative is 0 at that point or the derivative does not exist. One of those two things has to be true about the derivative. We call that a critical number. And so basically then what we can say is that, like it says on the top of page 273, box 6 there, that f has a local max or min at a point, then that point is going to be a critical number. So local maxes and mins only occur at critical numbers. And that's basically what we're saying there. So here's what we need to do then. The closed interval method to find absolute maximum values is basically going to be like that first example we looked at. And this is just the steps. Well, let's walk you through these steps on page 273. First thing you need to do is find the values of f at the critical points, or, well, the critical numbers of f. So any place where your derivative is 0 undefined. In this case, we had 4 places where our derivative was 0. So we'd want to find those places where our derivative is 0. We'll get some practice with that. We want to check the value of the function at those points. And then we also want to check the value of the function at the endpoints. And from those places, we're going to find our absolute max and absolute min. Remember, in this case, we found our absolute max was at a critical point, a critical number,